Hello everyone, I'm Xueli from Damo Academy Alibaba Group in China. I'm delighted to introduce our latest work, Flash, a framework for programming distributed graph processing algorithms. In today's world, we come across different types of graphs, such as social networks, road graphs, and smart city networks. Graph analytics algorithms enable us to discover valuable insights from these graphs. Over the years, various algorithms for graph processing such as clustering, centrality, traversal, matching, mining, and many more have been developed. As graph processing becomes increasingly important, many single machine and distributed graph processing models, frameworks, and DSLs have emerged. To comprehensively evaluate a graph processing framework, we consider three critical metrics: expressiveness, productivity, and efficiency. However, most of the recent graph processing frameworks only focus on a few fixed point, iterative single-phase and value propagation-based algorithms, which we call ISVP algorithms, while the distributed computation of a wide range of other algorithms suffers from low efficiency, limited expressiveness, or high implementation complexity with existing frameworks. So, how can we achieve all three EPE metrics for programming diverse graph algorithms in a distributed context? To address these challenges, we propose Flash. It is a novel high-level abstraction which provides succinct interfaces with strong expressiveness. We then provide an efficient implementation of Flash based on a novel design of the system architecture and a middleware named FlashWire. Currently, over 70 algorithms for over 40 problems have been implemented in Flash. According to our evaluation, the speed up over other works is up to 2 orders of magnitude, while it takes up to 92% less length of code for non-ISVP algorithms. This slide illustrates the comparison between Flash and other models in terms of expressiveness and productivity. We can see that Flash is capable of supporting all these algorithms, and it only takes tens of lines of code for programming each one. Further analysis reveals that Flash achieves strong expressiveness by supporting flexible control flow, operations on vertex sites, and beyond neighborhood communication. These features are not supported by any previous models. Flash achieves this by extending the programming model of Ligua to support beyond neighborhood communication and run in a distributed context. To be specific, Flash provides interfaces based on the vertex subset structure. The primary API is much similar to Ligua's, including size, vertex map, and edge map. It also provides some auxiliary operators for convenience. For example, to implement the classic vertex-centric BFS algorithm, we can use vertex map to initialize each vertex. Then, filter the set to pick up the root node, and iteratively use set and edge map to conduct updates on vertices step by step. By combining the primitives, Flash enables the definition of arbitrary control flow. The vertex subset structure supplements the perspective of a single vertex, allowing updates on arbitrary vertices. Finally, Flash allows users to define the edge set they want to transform messages, even if the edges do not exist in the original graph. We compared the efficiency of Flash with other frameworks, demonstrating that Flash outperforms others on the majority of applications. Flash achieves such high efficiency by using more advanced algorithms since it provides stronger expressiveness. Flash also improves efficiency through its architecture design and implementation. At first, we use a code generator to generate code to be executed by FlashWare from the high-level user-provided APIs. FlashWare is a middle layer that completes intranode updating and internode communication. It also enables some system optimizations. The first optimization is an adaptive switching between the push mode and the pull mode, according to the density of active vertex subset. It can lead to a performance enhancement over the push-only and pull-only alternatives. The second optimization is overlapping communication with computation by co-scheduling computation tasks and message passing. The third optimization is to synchronize only critical properties instead of all properties of a vertex. By reducing the size of a single message, it decreases the communication cost that improves performance. The last optimization is to communicate with only necessary partitions. For example, only its neighbors instead of all partitions. Also, a vertex may have mirrors on all partitions to support beyond neighborhood communication in Flash. This optimization improves performance by decreasing the total count of messages. We also evaluate the intranode and internode scalability of Flash, which shows a reasonable trend. In conclusion, we designed a new high-level programming model named Flash for programming diverse graph algorithms in a distributed context, and we then implement a new system for Flash with high efficiency. Flash is now a component of GraphScope, the framework for large-scale graph processing at Alibaba, and this version of implementation for Flash is open source at GitHub. That's all for my talk. Thanks for your attention.